What if our entire understanding of the cosmos is built on incomplete foundations? For centuries, humanity has gazed at the night sky, mapping constellations and charting the motions of celestial bodies, believing we've grasped the fundamental architecture of the universe. But what if some of the most profound structures out there don't just defy explanation, they shatter the very laws of physics as we know them? Imagine gazing into deep space and witnessing formations so bizarre, so inexplicable, that even our most advanced scientific models fall short. These aren't just mysteries, they're cosmic puzzles that force us to rethink reality itself. Today, we're setting out on a journey to explore 25 of the most astonishing cosmic structures ever discovered, phenomena that challenge everything from the nature of gravity to the fabric of spacetime. These aren't mere curiosities, they are monumental anomalies that have left researchers questioning long-held assumptions and racing toward new theories. Each one tells a story of wonder and bewilderment, inviting us to see the universe not as a settled expanse but as a dynamic, evolving frontier where the rules are still being written. This is more than a tour of strange sights, it's an invitation to witness the edges of human knowledge, where awe and inquiry collide. As we venture into the unknown together, you'll encounter colossal formations that warp light in impossible ways, vast cosmic voids where nothing should exist, and energetic anomalies that defy every prediction. This exploration isn't just about spectacle, it's about expanding our perspective and connecting with the profound mystery that lies at the heart of existence. You're about to see the universe in a whole new light, one that might just change how you see everything. So settle in, open your mind, and get ready to journey through the cosmos like never before. Our journey into the cosmic unknown begins close to home, relatively speaking, with a discovery so vast it seems to defy the very notion of a uniform universe. Imagine looking up at the night sky and tracing the familiar constellations, believing the stars are scattered more or less evenly across the infinite dark. This idea isn't just a feeling, it's a foundational pillar of cosmology known as the cosmological principle. It suggests that when you view the universe on a sufficiently large scale, matter should be distributed evenly in all directions, with no single region standing out as special or unique. It's the reason we feel confident making broad assumptions about the cosmos from our tiny vantage point. But what if we found something so enormous, so blatantly exceptional, that this entire principle began to crumble? That something is the Hercules-Corona Borealis Great Wall. This isn't a wall made of bricks and mortar, but a colossal filament, a sprawling river of galaxies, galaxy clusters, and dark matter that stretches across an almost incomprehensible 10 billion light-years. To put that staggering scale into perspective, the entire observable universe is about 93 billion light-years across. This single structure, this Great Wall, accounts for nearly a tenth of the entire observable cosmos. It is, by far, one of the largest single structures ever identified. Its discovery was a slow, meticulous process that involved mapping the locations of gamma-ray bursts. These are the most violent, energetic explosions in the universe, often signaling the death of massive stars or the collision of neutron stars. Because they are so intensely bright, they can be seen from incredible distances, acting like cosmic lighthouses. When astronomers began plotting their positions, they expected to see a random, scattered distribution, a sign of the universe's large-scale uniformity. Instead, they found a startling and immense concentration of these bursts, a dense, gigantic ribbon of structure arcing across the constellations of Hercules and Corona Borealis. The existence of such a behemoth directly challenges the cosmological principle. How can the universe be considered smooth and uniform when a structure of this magnitude exists? It's like assuming a vast ocean has a consistent texture, only to suddenly discover a single island chain so long it spans an entire hemisphere. This isn't just a minor anomaly, it's a fundamental problem. Our current models of the universe's evolution, based on the Big Bang theory, have a difficult time explaining how such an immense structure could have had enough time to form within the estimated age of the universe. Gravity simply shouldn't have been able to pull matter together over such vast distances in the time available. This forces astronomers into a fascinating dilemma. Either our understanding of the universe's infancy and the laws of gravity is incomplete, or we are misinterpreting our observations in some profound way. The Hercules-Corona Borealis Great Wall stands as a silent, monumental question mark in the sky, a reminder that the universe is far stranger and more complex than we ever imagined, and that our quest to understand its true architecture has only just begun. Just as we begin to wrap our minds around the immense scale of the Hercules-Corona Borealis Great Wall, our cosmic tour brings us to another titan that redefined what we thought was possible. This is the Sloan Great Wall, a structure so colossal that its discovery in the early 2000s sent shockwaves through the field of cosmology. Picture not a physical barrier, but a staggering concentration of matter, a sprawling superhighway of galaxies, clusters, and immense clouds of gas, all bound together by gravity into a single, ridiculously long filament. It stretches for approximately 1.37 billion light-years, a number so vast it can feel meaningless. To give that some grounding, if you could travel at the speed of light, a journey from one end of this wall to the other would take you over 1 billion years. It's a structure of such immense proportions that it easily dwarfs our local group of galaxies, containing thousands of times more mass and challenging our very notion of what constitutes a typical feature in our universe. The story of its discovery is a testament to the power of modern technology and ambitious sky surveys. This cosmic leviathan was uncovered by the Sloan Digital Sky Survey, one of the most detailed and comprehensive maps of the night sky ever attempted. Using a dedicated telescope in New Mexico, this project meticulously catalogued the positions and distances of millions of galaxies, creating an unprecedented three-dimensional atlas of our cosmic neighborhood. As astronomers pored over this new data, they weren't just seeing stars, they were seeing the large-scale structure of the universe itself, a cosmic web of filaments and voids. And within this web, one filament stood out from all the rest due to its sheer density and extraordinary length, an unmistakable and unexpected landmark in the vastness of space. The existence of the Sloan Great Wall presents a profound and nagging challenge to our most sophisticated models of cosmic evolution. According to our current understanding based on the lambda cold dark matter model, which is the standard model of Big Bang cosmology, the universe should have a certain statistical smoothness on the largest scales. While we expect filaments and nodes in the cosmic web, the probability of a single structure growing to the size of the Sloan Great Wall is incredibly low. It pushes right up against the theoretical limit of how large something could have grown given the age of the universe and the initial conditions set by the Big Bang. It's as if we found a single tree in a forest that was not just tall, but taller than the forest itself is wide. This forces cosmologists to ask difficult questions. Did something unusual happen in that specific region of space during the inflationary period immediately after the Big Bang, seeding it with a slightly denser concentration of matter that gave it a head start? Or could there be forces or influences at work on these gigantic scales that our current models of physics simply do not account for? The Sloan Great Wall is more than just a record holder. It is a crucial piece of evidence in an ongoing cosmic mystery. It doesn't just ask how such a structure formed, but compels us to reconsider the initial seeds from which all structure grew. By studying its properties, how its galaxies are clustered, how its mass is distributed, scientists are essentially performing a forensic investigation into the universe's earliest moments. Each massive structure like this acts as a fossil, preserving information about the forces that shape the cosmos. the wall's very presence suggests that our universe might be even more textured and complex on the grandest scales than we ever dared to imagine, hinting that the story of its birth and evolution is far from complete. But if the Hercules-Corona Borealis and Sloan Great Wall stretched our understanding of cosmic structure to its limit, the discovery of the Huge-LQG, or Huge Large Quasar Group, seemed to push it right over the edge. This isn't a wall of galaxies, but a colossal gathering of quasars, and it presents a problem so acute it sparked a fiery debate among cosmologists about the very foundations of their science. Quasars themselves are among the most luminous objects in the universe. They are the intensely bright cores of distant galaxies, powered by supermassive black holes actively feeding on surrounding matter, glowing with the light of 1 trillion stars and acting as beacons from the early universe. To find one is to look back in time. To find a group of them huddled together is to find a significant concentration of mass in the ancient cosmos. And to find the Huge-LQG is to find a gathering so vast and so dense that it appears to violate a fundamental rule of the universe. This structure, discovered in 2013, is a cluster of 73 quasars all bound within a region of space measuring an astonishing 4 billion light-years in its longest dimension. To grasp that scale, consider that the distance from our Milky Way to the nearest large galaxy, Andromeda, is a mere 2.5 million light-years. This single group of quasars spans a volume of space over 1,600 times that distance. It is a metropolis of unimaginable proportions, a gathering of cosmic giants that, according to our standard model of cosmology, simply should not be able to exist. The core of the problem lies with something known as the cosmological principle, the idea that on sufficiently large scales, the universe is smooth and homogeneous. This isn't just a philosophical concept, it's the bedrock upon which virtually all of modern cosmology is built. It allows scientists to apply the laws of physics uniformly and make sense of what we see when we look out into the depths of space. The established limit for this principle, the maximum size a structure should theoretically be able to reach, is around 1.2 billion light-years. The Huge-LQG smashes through that limit at more than 3 times that size. Its very existence suggests that the universe might not be smooth and uniform on the largest scales after all, but rather lumpy and textured in ways we never predicted, filled with structures so immense they defy our current physical models. This discovery ignited a profound debate within the astronomical community. One camp argues that the Huge-LQG is a death knell for the cosmological principle, a clear piece of evidence that we need to radically overhaul our understanding of the universe's architecture. They point to its staggering size and the statistical near impossibility of it forming by random chance under the old rules. The other camp suggests that what we're seeing might be a trick of perspective, that these quasars may not be physically connected in a single, bound structure, but could instead be aligned along our line of sight by chance, creating a phantom pattern in the data that doesn't reflect a true physical anomaly. This counter-argument hinges on the challenges of mapping a 3-dimensional universe from our single, fixed viewpoint, a process always susceptible to certain biases. Yet, even with that caveat, the Huge-LQG remains a monumental puzzle. Its discovery forces us to confront the limitations of our models and the potential for our own biases to shape what we think we know. It serves as a powerful reminder that the universe is under no obligation to conform to our human sense of order and uniformity. Whether a real structure or a cosmic mirage, the Huge-LQG challenges us to look deeper, to question our most basic assumptions, and to consider the thrilling possibility that the cosmos is far stranger and more wondrous than our principles have so far allowed. If the great walls and quasar groups represent the crowded metropolises of the cosmos, then our next destination is the universe's most desolate and haunting wilderness. After contemplating structures of unimaginable density, we now turn to a place defined by its breathtaking absence, Imagine looking out at the night sky and knowing that within a certain patch of darkness there is almost nothing at all. Not just an empty closet, but an empty skyscraper. Not just an empty field, but an empty continent. This is the essence of the Boots Void, a region of space so profoundly empty that it has earned the ominous nickname the Great Nothing. Spanning a colossal sphere of space approximately 330 million light-years across, the void is a staggering cosmic desert. To appreciate the sheer scale of this emptiness, consider that our entire Milky Way galaxy would be a mere speck within it. If you were to place the Milky Way at one edge of the void, the distance to the other side is so vast that light, the fastest thing in the universe, would take over 300 million years to make the crossing. And within this incomprehensible volume, astronomers have found only a handful of galaxies, where a region of space this size should contain thousands upon thousands of galaxies. The Boots Void holds perhaps 60. The overwhelming majority of this volume is just nothing. This profound emptiness presents a direct and puzzling contradiction to our models of the universe's large-scale structure. The prevailing lambda-cold dark matter model does predict that the cosmic web should have holes or voids within it. Gravity pulls matter into the dense filaments and clusters, naturally leaving behind less dense regions. But the Boots Void is not just a hole, it is a chasm. Its size is so extreme that it falls far outside the predicted statistical norms for such structures. It's as if you expected to find a few potholes on a road, but instead discovered a single, gaping sinkhole large enough to swallow an entire city. Its existence forces cosmologists to ask a deceptively simple question: how did it get so empty? Several compelling theories attempt to explain the void's origin, each more fascinating than the last. One leading idea suggests that the void is not truly empty, but is instead dominated by a preponderance of dark energy, the mysterious force accelerating the universe's expansion. In this region, dark energy may have gained an early upper hand, causing space itself to stretch and expand at a faster rate than elsewhere, effectively pushing matter apart and preventing galaxies from forming. The void isn't empty because matter was removed. It's empty because the very fabric of that space was stretched thin from the very beginning. Another, more dramatic theory involves a cosmic collision of a different sort. Some scientists speculate that the Boots Void could be the result of not one, but many smaller voids merging together over billions of years. Imagine bubbles in a sink of water slowly coalescing into one giant bubble. As the universe evolved, smaller underdense regions could have gravitationally influenced each other, their boundaries dissolving until they fused into the single, gigantic void we observe today. This process would have swept the area clean, herding the sparse matter that remained toward the edges. There's even a more speculative yet thrilling possibility that the void is evidence of an encounter with a parallel universe. In some exotic models of the multiverse, the gravitational tug of a neighboring universe upon our own could potentially create a vast, empty region in the space between them. While this remains firmly in the realm of theoretical physics, the very fact that such an idea is even entertained highlights just how mysterious and challenging the Boots Void truly is. It stands as a silent, dark monument to the fact that in cosmology, nothing can be just as profound and illuminating as something. But how do we even begin to map such a vast emptiness? Our next destination is not found by looking at the absence of galaxies, but by studying the oldest light in the entire cosmos, a faint, cold echo from the very dawn of time. After exploring the great nothing of the Boots Void, we turn our attention to a chill in the universe's background radiation that has sparked one of the most thrilling and controversial debates in modern cosmology. This is the story of the cold spot in the cosmic microwave background. The cosmic microwave background, or CMB, is often called the afterglow of the Big Bang. It is the remnant heat from the birth of the universe, cooled and stretched over 13.8 billion years into a faint microwave glow that uniformly permeates all of space. Mapping this radiation is like taking the universe's baby picture, and this picture is remarkably smooth, with only tiny, random variations in temperature. These fluctuations are the seeds from which all future structure galaxies, clusters, and great walls would eventually grow. So, when astronomers created exquisitely detailed maps of this CMB, they expected to see a universe that was fundamentally uniform in its infancy. What they did not expect to find was a glaring anomaly, a cold region so large and so statistically unlikely that it seemed to defy explanation. The cold spot is not just a slightly cooler patch. It is a colossal circular region in the constellation Eridanus, spanning over 1.8 billion light-years across, where the temperature of the microwave background is significantly colder than the surrounding area. The odds of such a pronounced and coherent cold spot appearing randomly in the otherwise smooth CMB are astronomically low, less than 1 in 200. Its presence suggests that something significant happened in that part of the sky, something that left a permanent mark on the fabric of the universe. Scientists have proposed two primary explanations for this mysterious chill, and both are extraordinary. The first, more conventional theory suggests the cold spot is a shadow cast by a cosmic supervoid. The idea is that between us and the CMB lies an immense, underdense region of space, even larger than the Boots void. As light from the CMB travels through this void on its way to our telescopes, it must climb out of the void's gravitational well. According to Einstein's theory of general relativity, light loses energy as it climbs out of a gravitational potential, a phenomenon known as the integrated Sachs-Wolfe effect. This loss of energy would cause a slight redshifting of the light, which we would observe as a cooling of the CMB in that direction. In this scenario, the cold spot is a cosmic mirage, a shadow of a great nothing. The search for this proposed supervoid, however, has yielded conflicting results. Some surveys have indeed found evidence of a large underdense region in the general direction of the cold spot, but its size and emptiness don't seem quite sufficient to account for the dramatic temperature drop. This discrepancy has led to the second and far more speculative explanation, that the cold spot is evidence of a collision with another universe. This idea springs from the theory of eternal inflation and the multiverse, which suggests our universe is just one bubble in a vast, frothing cosmic foam of innumerable other bubble universes. In this breathtaking model, the cold spot could be the bruise left from a collision between our universe and a neighboring bubble universe in the distant past. The physics of such a collision would be unlike anything we know, but theorists suggest it could have transferred energy out of our region of space-time, effectively sucking energy away and leaving behind a cold imprint in the CMB. While this remains a highly speculative hypothesis, the very fact that it is a subject of serious scientific discussion underscores just how perplexing this feature truly is. The cold spot forces us to confront the limits of our knowledge, presenting us with a choice between a strangely inadequate void or evidence for a reality far grander than we ever imagined. It is a tantalizing cosmic clue, a cold case that remains wide open. And just as we grapple with the implications of a cold spot that could be a cosmic bruise, our journey through the cosmos reveals another structure that seems to bend the rules of reality itself. This isn't a wall or a void, but a graceful, almost artistic curve etched across the heavens, a formation so vast and so perfectly arced that its very shape seems to defy the randomness of the universe. This is the Giant Arc, a recently discovered celestial landmark that is forcing us to question one of astronomy's most deeply held beliefs. Discovered in 2021 by astronomer Alexia Lopez while analyzing the light from distant quasars, the Giant Arc is a monumental arrangement of galaxies, galaxy clusters, and intergalactic gas. It forms a near-symmetrical crescent that spans an astounding 3.3 billion light-years across the constellation of Boötes, the herdsman. To visualize such an impossible scale, imagine a structure so large that it would take light, the fastest thing in the known universe, over 3 billion years to travel from one tip of the arc to the other. If you could somehow see it in the night sky, it would stretch the length of 20 full moons, a breathtaking sweep of cosmic architecture. What makes the giant arc so profoundly challenging isn't just its immense size, but its coherent, organized shape. The standard model of cosmology, guided by the cosmological principle, posits that matter in the universe should be distributed more or less evenly and randomly on the largest scales. We expect a cosmic web, a tangled, fractal-like network of filaments and nodes, not a single, sweeping curve that appears to follow a specific, organized pattern. The arc's distinct form suggests a level of large-scale structure and organization that our current models simply do not predict and cannot easily explain. It's as if you tossed a handful of sand onto a table and it somehow arranged itself into a perfect, recognizable symbol. The statistical unlikelihood of this structure forming by pure chance is staggering. Analysis shows that the probability of such a well-defined gigantic arc appearing in a random distribution of matter is less than 0.0003%. This isn't just a minor anomaly, it is a 5 sigma-level discovery, the same gold standard used to confirm the existence of new particles like the Higgs boson. In the world of physics, that level of statistical significance is a deafening alarm bell, signaling that something in our fundamental understanding is either missing or incorrect. This places the giant arc squarely in the company of other massive anomalies like the Hercules-Corona Borealis Great Wall, collectively pointing toward a potential crisis in cosmology. Could the cosmological principle, a foundation of modern astronomy, be flawed? The principle assumes no single location or direction in the universe is special, but the giant arc, located in a specific region of the sky with a specific shape, feels very much like a special place. Its existence suggests that the universe might not be homogeneous and isotropic after all, but could possess a much larger, more intricate architecture than we have ever dreamed of. The discovery pushes cosmologists to explore radical new ideas. Some theories propose that the arc could be a remnant of a feature from the universe's very first moments, a fossilized imprint from a period of rapid inflation that seeded an unusual density wave into the fabric of space-time. Others speculate it could be related to the mysterious nature of dark matter or dark energy, hinting that their influence might not be uniform but could vary across the cosmos, sculpting matter into unexpected forms. The giant arc is more than just a list of numbers. It is a profound question mark written across the sky, a curve that challenges the straight lines of our scientific models and invites us to imagine a cosmos far more wondrous and structured than we ever believed possible. While the giant arc presents a challenge to our ideas of cosmic structure through its immense and organized shape, our next discovery questions the very motion of the universe itself. We now turn to one of the most unsettling and profound mysteries in modern cosmology, a phenomenon known as the dark flow. Imagine the entire universe is expanding from the Big Bang, with galaxies drifting apart in a generally uniform manner, like raisins in a rising loaf of bread. This expansion, known as the Hubble flow, is the dominant motion of the cosmos. But what if you discovered that thousands of massive galaxy clusters weren't just riding this expansion? What if they were all moving together in a specific, coordinated direction, as if being pulled by some unseen force? This isn't science fiction. It's the startling evidence that has emerged from careful observations of the cosmic microwave background. The story of the dark flow begins not with visible light, but with the faint microwave glow that fills the universe. The hot and cold spots in the cosmic microwave background are not just fossils. They can also be used as a cosmic reference frame, scientists realized they could use a subtle effect called the kinematic Sunyaev-Zeldovich effect to measure the motion of enormous galaxy clusters relative to this background. As these massive clusters move through space, the hot electrons within their gas scatter the photons of the CMB. If a cluster is moving toward us, the scattered photons appear very slightly warmer. If it's moving away, they appear very slightly colder. It's an exquisitely delicate measurement, like trying to detect a single warm breath on a cold, windy day from miles away. A team led by astronomer Alexander Kashlinsky began making these measurements, expecting to find random, small motions that averaged out to zero, perfectly aligning with the Hubble flow. Instead, they found something that defied all expectations. They detected a consistent, coherent flow of hundreds of clusters all moving in the same direction at astonishing speeds of nearly 2 million miles per hour. This wasn't a local effect. The flow was detected in clusters billions of light years away, across a vast sweep of the sky. It was as if a colossal, invisible hand was pushing or pulling these titanic structures on a universal scale. The most perplexing aspect of the dark flow is its apparent source. The motion is directed toward a specific point in the constellations of Centaurus and Vela, but there is nothing there of sufficient mass to explain this gravitational pull. Not a supercluster, not a great wall, nothing within our observable universe is large enough to exert such a force. This leads to the only conclusion that fits the data, yet sounds like it's straight from the realm of theoretical fantasy. The pull must be coming from something outside our observable universe. This idea is as revolutionary as it is unsettling. The observable universe is the spherical volume of space from which light has had time to reach us since the Big Bang, a region about 93 billion light-years across. The dark flow suggests that beyond this horizon, there exists a concentration of mass so unimaginably enormous that its gravitational influence can reach across the void and tug on entire galaxy clusters within our own cosmic bubble. This mass could be a vast, exotic structure made of types of matter we've never seen, or it could be the gravitational influence of another universe entirely, residing in a multiverse of cosmic bubbles. The implications of this are staggering. If confirmed, the dark flow would be the first empirical evidence that our universe is not all there is. It would provide a tantalizing glimpse into the cosmos beyond our cosmic horizon, suggesting that the grand structure of reality is far vaster and more complex than we ever imagined. The phenomenon remains controversial, with some scientists proposing alternative explanations involving subtle biases in the data or unknown local effects. Yet, subsequent studies have continued to find evidence supporting this mysterious flow. The dark flow stands as a profound challenge, a cosmic current hinting at uncharted territories and realities lying just beyond the edge of everything we can see, pulling us toward a future of even deeper discovery. If the dark flow hints at a mysterious pull from beyond our cosmic horizon, then the Great Attractor is a gravitational enigma much closer to home, a force so powerful it is literally dragging our entire galaxy and everything around us on a relentless journey through the cosmos. We are not stationary observers in a static universe. We are passengers on a spacecraft called the Milky Way, and we are moving at an astonishing speed of over 1 million miles per hour. But we are not simply drifting with the universal expansion. We are being pulled with thousands of other galaxies toward a specific, unseen point in the constellation Centaurus. For decades, the source of this immense gravitational pull was one of astronomy's most frustrating mysteries, hidden from our view by a cosmic curtain known as the zone of avoidance. This zone isn't a physical barrier but a region of the sky obscured by the dense disk of our own Milky Way galaxy. When we look toward the center of our galaxy, we are looking through a thick fog of stars, gas, and cosmic dust that blocks our optical view of the universe beyond. It's like trying to see a distant city through the heart of a blinding storm. For the longest time, whatever was exerting this incredible gravitational force on us lay directly behind this impenetrable veil, leaving astronomers to theorize with little direct evidence. They named this unseen focal point of our motion the Great Attractor, a title that perfectly captures its powerful and mysterious nature. The first clues to its existence came from mapping the peculiar velocities of galaxies, their motions that deviate from the smooth expansion of the universe. Everywhere we looked, galaxies in our local supercluster were streaming toward this one spot. The sheer scale of the motion implied an absolutely colossal concentration of mass, something on the order of tens of thousands of Milky Ways, all packed into a region of space about 300 million light-years across. The hunt was on to see the unseeable. How do you study something you cannot directly observe? The answer lay in looking with different eyes. Astronomers turned to telescopes that could peer through the galactic dust using wavelengths of light it cannot block, such as radio waves and infrared light. This technological breakthrough finally began to lift the veil. Projects like the Parkes Radio Telescope surveys started to map the galaxies hidden behind the Milky Way's bulge, and what they found was astounding. The Great Attractor wasn't a single, unimaginably dense object. It was instead the heart of a much larger structure, the Laniakea Supercluster. Laniakea, which means immeasurable heaven in Hawaiian, is the gravitational home of our own Milky Way galaxy and over 100,000 others. The Great Attractor is essentially the central gravitational valley of this vast supercluster, a dense core where the pull of numerous massive galaxy clusters, like the Norma cluster, combines into a single powerful force. It is the downtown, the metropolis of our local cosmic continent, and we are all flowing toward its center. But even with this discovery, a puzzle remains. While the mass of these visible galaxies is immense, it still doesn't fully account for the tremendous gravitational pull we experience. This is where the story of the Great Attractor dovetails with one of cosmology's greatest mysteries, dark matter. The shortfall in visible mass suggests that the true engine of this gravitational anomaly is a huge, concentrated halo of this invisible substance. The Great Attractor, therefore, is likely a massive knot in the cosmic web of dark matter, its hidden gravitational scaffolding orchestrating the motion of galaxies across millions of light-years. Its discovery and subsequent investigation provide some of the most compelling real-world evidence for how dark matter shapes the large-scale structure of the universe, acting as the hidden architecture upon which the visible cosmos is built. The implications are profound. Our journey toward the Great Attractor reminds us that we are part of a dynamic, interconnected cosmic flow, bound by gravity to structures far grander than we can see with the naked eye. It underscores a humbling truth. Even our place in the universe is in motion, guided by forces both visible and unseen, on a voyage toward a destination we once could not see but are now slowly beginning to understand. Yet this grand journey toward the Great Attractor and our place within the Laniakea Supercluster presents a profound and deeply personal irony, one that reshapes our understanding of our own cosmic address. We might assume that residing in such a massive supercluster means we are living in a fairly average, representative region of the universe, but startling evidence now suggests the opposite may be true. We may, in fact, be residing in one of the universe's great deserts, a vast cosmic void now known as the KBC Void, named after the researchers Keenan, Barger, and Cowie who identified it. This discovery doesn't just change our galactic zip code, it forces us to reconsider some of the most fundamental measurements in all of cosmology. The KBC Void is a staggering spherical region of space, approximately 2 billion light-years in diameter, with our Milky Way galaxy sitting right near its center. It is not a complete emptiness like the Boots Void, but rather a significant underdensity, a region where the concentration of matter, including galaxies and galaxy clusters, is about 20% lower than the average density of the universe at large. To visualize this, imagine the cosmos as a landscape of towering mountain ranges, rolling hills, and deep valleys. For decades, we thought we were on a hill, perhaps even a modest mountain. The KBC void suggests we are actually sitting in a very wide, shallow valley, and our view of the distant universe is filtered through this sparse local environment. This seemingly minor detail of our location has earth-shattering implications for one of the most critical numbers in science, the Hubble constant. This is the rate at which the universe is expanding, a figure astronomers have been trying to pin down with ever-increasing precision. There are two primary methods for measuring this expansion. One involves looking at the local universe using relatively nearby objects like Cepheid variable stars and supernova to gauge how fast galaxies are receding from us. The other method looks back to the very beginning, studying the cosmic microwave background to see what the expansion rate should be based on the universe's initial conditions. These two methods, despite incredible advancements, have persistently yielded different results. This discrepancy is known as the Hubble tension, and it represents one of the most significant unsolved problems in modern cosmology. The existence of the KBC void offers a compelling and elegant solution to this tension. If we are indeed residing in a giant underdense region, it would profoundly affect our local measurements of the Hubble constant. Here's why, in a void where there is less matter, the gravitational pull holding space together is weaker. This means that the space within our local void is actually expanding faster than the global average. The empty stretches between galaxies are being stretched more vigorously because there's less gravity to counteract the push of dark energy. When we use nearby supernova to measure the expansion, we are measuring this faster local rate. However, the CMB method measures the global average expansion rate, which is slower because it incorporates the effects of all the dense regions and filaments outside our void that are gravitationally tugging on spacetime and slowing the expansion down. In essence, we have been comparing apples to oranges. Our local measurement is like calculating the speed of a car on a long, empty downhill stretch of highway, while the CMB measurement gives us the average speed for the entire cross-country journey, which includes traffic jams, mountain climbs, and city streets. Both measurements are correct, but they are describing different things because of our unique location in a cosmic valley. The void isn't a flaw in the data, it is the key to understanding it. This realization could resolve the Hubble tension not by finding an error in our meticulous observations, but by adding a crucial layer of context about our place in the cosmos. The implications of this are philosophically humbling. For centuries, since Copernicus dethroned Earth from the center of the universe, we have operated under the assumption that our vantage point is not special or privileged. The KBC void challenges this Copernican principle in a subtle but profound way. While we are not at the center of the universe, we may be at the center of a very large, atypical region of it. This doesn't make us special, but it does make our perspective unique, and it forces us to account for our local environment when we try to describe the entire cosmos. It is a powerful reminder that to truly understand the universe, we must first understand our own place within its grand and textured architecture. If the KBC void redefined our local neighborhood as an underdense valley, then the Laniakea Supercluster is the immense gravitational continent that contains it, offering a breathtaking new perspective on our place in the cosmos. For generations, we understood our cosmic address in a simpler way. We lived in the Milky Way galaxy, which was part of a small local group, which in turn was a component of the Virgo supercluster. This was our home, a structure we believed we understood, but a revolutionary new mapping technique has completely rewritten this address, revealing that the Virgo supercluster is not a distinct entity at all, but merely a lobe, an appendage of a structure of such staggering grandeur it was given a name meaning immeasurable heavens in Hawaiian, Laniakea. This discovery didn't come from a new telescope capturing a stunning image, but from a profound shift in how we measure the universe's structure. Instead of just plotting the locations of galaxies in space, astronomers led by R. Brent Tully at the University of Hawaii focused on their motions. They realized that to understand the true architecture of the cosmos, you cannot just look at where galaxies are, you must watch where they are flowing. By painstakingly calculating the peculiar velocities of thousands of galaxies, that is, their individual movements after subtracting the general expansion of the universe, the team was able to trace the gravitational watersheds of intergalactic space. They were effectively mapping the universe's gravity rivers, and in doing so, they uncovered the true bounds of our home supercluster. Laniakea is a gravitational metropolis of unimaginable scale, a vast network of over 100,000 galaxies stretching across 520 million light-years. At its heart lies the Great Attractor, the gravitational anchor we discussed earlier. All the galaxies within Laniakea, including our own Milky Way, are flowing inward toward this central gravitational valley. The boundaries of this supercluster are not defined by empty space, but by the points where this flow diverges, where galaxies stop moving toward the Great Attractor and begin flowing toward other, neighboring superclusters. It's akin to mapping a continent by finding the mountain ridges where rainwater stops flowing toward one ocean and starts flowing toward another. We are not just near the Great Attractor, we are permanently bound to it, caught in its immense gravitational pull along with 100,000 other island universes. This new understanding fundamentally challenges our previous notions of galactic organization. The old Virgo supercluster wasn't wrong, it was just myopic. It was like identifying your street and assuming it was the entire city. Laniakea reveals the true city, showing that what we once thought were separate superclusters are actually interconnected parts of a single, vastly larger structure. It redefines our local universe not as a collection of isolated clusters, but as a continuous, dynamic flow of galaxies on a scale that is difficult to comprehend. Our entire local group is on a relentless journey, not as a solitary ship, but as one vessel in a colossal armada of galaxies, all navigating the same cosmic currents toward a common destination. The discovery of Laniakea does more than just give us a new name for home. It provides a crucial framework for understanding the large-scale forces that govern our motion and ultimately our fate. It illustrates the overwhelming influence of dark matter, whose invisible scaffolding dictates the flow of all visible matter. By mapping where galaxies are going, we are indirectly mapping the distribution of this mysterious substance, revealing the hidden architecture that binds the universe together. Laniakea is the ultimate expression of our interconnected cosmos, a humbling reminder that we are part of a grand gravitational dance whose steps are only just beginning to be learned. But just as we've begun to map the gravitational flows of Laniakea, another, even larger structure was lurking in the shadows, hidden from our view in a way that makes the zone of avoidance seem like a minor inconvenience. If mapping the Great Attractor was like seeing through a fog, then discovering the South Pole Wall was like finding a hidden continent on the other side of the world, concealed behind an impenetrable mountain range. This is a structure of such colossal proportions that its discovery required not just new telescopes, but a completely new way of seeing the universe. Stretching an almost unbelievable 1.4 billion light-years across the southern celestial sphere, the South Pole Wall is a gargantuan filament of galaxies, one of the largest known structures in the observable universe. To grasp its scale, consider that it is longer than the diameter of the entire Laniakea supercluster, a behemoth that utterly dwarfs our own galactic neighborhood. And yet, for all its immensity, it remained hidden from us because a significant portion of it lies directly behind the central bulge of our own Milky Way, an area even more obscured than the zone of avoidance we encountered with the Great Attractor. This region is so dense with stars, gas, and dust that it completely blocks our optical view, creating a massive blind spot in our maps of the cosmos. Its discovery, announced in 2020, is a masterpiece of cosmological detective work. Astronomers couldn't see the wall directly, so they had to infer its presence by observing its gravitational effects. The team, led by cosmographer Daniel Pommard, used a technique that maps the peculiar velocities of galaxies, the same method used to define Laniakea. By meticulously tracking the subtle motions of thousands of galaxies in the southern sky, they could trace the rivers of gravitational influence, just as a hidden planet can be discovered by the wobble it induces in a star's motion. The immense mass of the South Pole Wall was revealed by the way it was pulling galaxies toward it, creating a distinct pattern in their cosmic flow. This data was then combined with other surveys to create a three-dimensional map of the distribution of both visible and dark matter, finally revealing the Chinese letter of the hidden giant. The existence of such a structure pushes our models of cosmic evolution to their absolute limits. Like the other Great Walls we've explored, the South Pole Wall's sheer size challenges the cosmological principle and the theoretical upper bound on how large a single structure can grow. The universe is 13.8 billion years old, and there is only so much time for gravity to pull matter together over such mind-boggling distances. The presence of the South Pole Wall suggests that the initial conditions of the universe, the seeds planted during the inflationary epoch, must have had incredibly pronounced density variations on scales we are only just beginning to appreciate. It forces us to consider that the cosmic web might be woven with threads far thicker and longer than our simulations have ever predicted. Furthermore, its location adds a fascinating layer to our understanding of the local universe's dynamics. The South Pole Wall is not an isolated structure. It is a major player in the gravitational field that influences the motion of our own local group of galaxies. Its immense pull contributes to the complex web of forces that includes the Great Attractor and the broader Shapley Supercluster, acting as a counterweight that helps shape the specific velocity of our Milky Way. Discovering it is like finally identifying a major mountain range that we knew had to be there because of the way all the rivers in a continent flowed. Its presence completes our picture of the local cosmic landscape, revealing that the forces guiding our journey are even more complex and far-reaching than we had ever imagined. It stands as a testament to human ingenuity, a hidden giant revealed not by sight, but by its undeniable gravitational signature. While the South Pole Wall revealed a hidden structure through its gravitational influence, our next discovery announces its presence not with a gentle pull, but with a violent, brilliant scream of high-energy light. After mapping the silent, dark architecture of the cosmos, we now turn our attention to a spectacle of raw power emanating from the very heart of our own galaxy. This is the story of the Fermi bubbles, two colossal spheres of searing hot gas and intense radiation that balloon out from the Milky Way center, stretching for 25,000 light-years above and below the galactic plane. If you could see them in gamma-ray light, they would dominate the southern sky, each bubble appearing 15 times wider than a full moon, a breathtaking and terrifying monument to some ancient cataclysm. Their discovery was a triumph of modern astronomy and a lesson in how much we have yet to learn about our own cosmic backyard. They were first detected in 2010 by NASA's Fermi Gamma-Ray Space Telescope, an instrument designed to scan the heavens for the most energetic photons in the universe. As scientists meticulously processed the data from Fermi's Large Area Telescope, they had to carefully subtract all the known sources of gamma rays, the pulsars, the distant quasars, the diffuse glow from cosmic ray interactions. What remained was something utterly unexpected, a gigantic hourglass-shaped structure of gamma-ray emission, with its narrow waist centered perfectly on the supermassive black hole at our galaxy's core, Sagittarius, a star. These weren't faint wisps, they were bright, well-defined and immense, a pair of cosmic exhaust fumes left over from a titanic event. The sheer energy contained within these bubbles is what makes them so astounding and so challenging to explain. The gas within them is not the cold, quiet matter of interstellar space. It is a superheated plasma raging at millions of degrees. To inflate these bubbles to their current size and to heat the gas within them requires a sudden, tremendous injection of energy, equivalent to the simultaneous explosion of 100,000 supernovae. The central question that has captivated astrophysicists ever since is this: what engine in our galaxy could possibly produce such an unimaginable outburst? Two primary theories have emerged, each more dramatic than the last. The first and leading theory points to a past period of extreme gluttony by our galaxy's central black hole, Sagittarius, a star. Today, our supermassive black hole is relatively quiet and dim, a sleeping giant, but the Fermi bubbles suggest it may have had a violent waking period in the relatively recent past, perhaps as little as 2 to 3 million years ago. During this active phase, known as an AGN or active galactic nucleus event, vast quantities of matter, gas, dust, even stars would have spiraled into the black hole's accretion disk. As this matter was compressed and heated to incredible temperatures, it would have generated powerful jets of radiation and particles, shooting out from the black hole's poles at nearly the speed of light. These jets could have punched through the galactic gas above and below the plane, inflating the bubbles and filling them with hot, high-energy plasma. In this scenario, the bubbles are the fossilized remnants of a monumental black hole-feeding frenzy. The second theory ventures into even more exotic territory, proposing that the bubbles are evidence of dark matter annihilation. This idea suggests that the dense concentration of dark matter believed to surround the galactic center could be the key. If dark matter particles are their own antimatter counterparts, as some theories propose, then when two of them collide, they could annihilate each other in a flash of pure energy, producing standard model particles like electrons and protons, as well as gamma rays. A sudden, cataclysmic cascade of such annihilations in the galactic core could have provided the immense energy needed to blow the bubbles. While this remains a more speculative hypothesis, it is thrilling because it offers a potential way to indirectly observe and study the properties of this mysterious substance that makes up most of the matter in the universe. The existence of the Fermi bubbles forces a significant re-evaluation of our galaxy's history and dynamics. We can no longer view the Milky Way as a stable, sedate spiral. Its recent past was evidently punctuated by episodes of incredible violence that have left permanent scars on its structure. These bubbles are not static sculptures, they are ongoing phenomena. Their edges are sharp, suggesting they are still expanding into the surrounding galactic halo, and they are surrounded by a faint shell of cooler, radio-emitting gas known as the Milky Way's microwave haze. Studying them is like conducting an archaeological dig on a galactic scale, uncovering clues about a transformative event that occurred long before humans walked the Earth, but whose magnificent aftermath is still visible today. A pair of silent, glowing giants standing guard over the Milky Way. While the Fermi bubbles reveal a violent history written across our own galaxy, our journey now takes us to a structure of such serene and perfect beauty that it seems almost too harmonious to be real. If the universe is often a place of chaotic collisions and turbulent flows, then Hoag's object is a stunning exception, a cosmic eye staring back at us from across the void with an almost hypnotic symmetry. Discovered by astronomer Art Hoag in 1950, this enigmatic galaxy appears as a nearly perfect ring of brilliant blue, young stars encircling a calm, golden-yellow core of older stars, with a seemingly complete and utterly dark gap separating the two. It is a celestial bullseye, a structure so aesthetically flawless that it feels more like a work of art than a natural astronomical phenomenon, defying everything we know about how galaxies are supposed to form and evolve. The mystery of Hoag's object lies in its profound isolation and its perplexing structure. Most galaxies fall into familiar categories: spirals with their winding arms, ellipticals that are featureless blobs, or irregulars that are messy and chaotic. Hoag's object fits none of these. Its core resembles a classic elliptical galaxy, but it is surrounded by that perfect, detached ring, with no visible sign of any connecting material or the central bar structure typically seen in barred ring galaxies. To make the puzzle even deeper, subsequent observations have revealed that the ring itself is not a single structure. It is actively forming new stars at a prodigious rate, evidenced by its vibrant blue hue, which is the signature color of hot, massive young stars. The core, by contrast, is composed of cooler, older, redder stars with very little recent star formation. This creates a galaxy of two distinct generations, a celestial dichotomy that is both beautiful and baffling. Scientists have proposed several theories to explain this cosmic rarity, but each one comes with its own set of challenges. The most favored explanation is that Hoag's object is the result of a rare and precise galactic collision. Billions of years ago, a smaller dwarf galaxy might have shot directly through the heart of what was then a more conventional galaxy. This bullseye impact would have sent powerful density waves rippling through the victim galaxy's disk, much like a pebble dropped in a pond. These waves would have compressed gas and dust in their wake, triggering a spectacular burst of star formation in a perfect circular ring, while leaving the central core relatively undisturbed. Over eons, the intruder galaxy would have continued on its way, leaving behind this perfect ring as the only evidence of its violent passage. This bullseye collision theory is compelling, but it requires an incredibly specific set of circumstances, a direct perpendicular hit, making such objects extraordinarily rare in the cosmos. An alternative and even more intriguing possibility is that Hoag's object is an example of an extremely unstable form of galaxy that underwent a spontaneous internal transformation. In this resonance theory, the galaxy's own gravitational dynamics, perhaps influenced by a past minor interaction, became unstable. This instability could have caused the outer disk to resonate, collapsing inward to form a dense ring while the inner regions contracted to form the core, with a gap between them representing a region where gravitational forces prevent stars from forming or settling. This would make it a peculiar and short-lived phase in galactic evolution, a snapshot of a galaxy rearranging itself, caught in a brief moment of perfect but transient equilibrium. What makes Hoag's object even more fascinating is that it isn't entirely alone. In the vast dark gap between its brilliant ring and central core, follow-up observations with the Hubble Space Telescope revealed something wondrous, another, even more distant ring galaxy, seen perfectly through the gap. This incredible alignment suggests that such structures, while immensely rare, might be more common than we think, lurking throughout the universe as hidden celestial jewels. Hoag's object challenges the very classification system we use for galaxies, forcing us to acknowledge that the universe has more tricks up its sleeve than our simple categories can contain. It stands as a quiet, elegant reminder that cosmic beauty and mystery are often one and the same, a perfect ring of starlight whose origins continue to orbit the edges of our understanding. Yet, even as we marvel at the visible beauty of a structure like Hoag's object, we are forced to confront a humbling truth. The stars and gas we can see are merely the glittering decoration on a far more massive, invisible framework. This brings us to perhaps the most profound and pervasive cosmic structure of all, one that we cannot see, touch, or directly measure, but whose influence governs the motion of every galaxy we have discussed so far. We are talking about the vast, intricate network of dark matter halos, the hidden skeleton upon which the entire visible universe is built. The story of their discovery begins not with a telescope image, but with a discrepancy in the math. In the 1930s, Swiss astronomer Fritz Zwicky was studying the Coma cluster, a huge gathering of galaxies. By measuring how fast these galaxies were orbiting the cluster's center, he could calculate the total mass needed to provide the gravitational glue to hold it all together. The number he arrived at was staggering. The mass required was hundreds of times greater than the mass of all the visible stars and gas he could count. He called this missing mass dunkle materie, or dark matter, and while his work was largely ignored for decades, it planted the seed for a revolution in our understanding of the cosmos. This revolution gained irrefutable momentum with the work of astronomer Vera Rubin in the 1970s. By meticulously measuring the rotation curves of spiral galaxies, that is, how fast stars orbit around a galactic center, she found something that defied the laws of gravity as we knew them. According to Kepler's laws, stars on the outer edges of a galaxy should orbit much more slowly than those near the center, just as Pluto orbits the Sun much more slowly than Mercury. But Rubin found that stars far out in the galactic suburbs were orbiting just as fast as those downtown. The only possible explanation was that each galaxy was surrounded by a gigantic, massive sphere of something invisible, a dark matter halo whose gravity was keeping those high-speed stars from flying off into intergalactic space. These halos are not simple clouds, they form an immense, interconnected cosmic web, a scaffolding of invisible mass that stretches across the entire universe. This is the true large-scale structure of the cosmos. The great walls, the superclusters, the filaments, all of these visible features trace the densest regions of this dark matter web, like froth on the peaks of ocean waves. The galaxies we see are simply where enough ordinary matter has been able to pool and cool within the deep gravitational wells created by these dark matter knots. The voids, like boots, are the empty spaces in the web where the dark matter is less dense. Understanding the properties of these halos is the key to unlocking the mystery of dark matter itself. We know what dark matter is not. It is not black holes made of ordinary matter. Their gravitational signatures don't match. It is not clouds of cold gas. We would see them. It is not a population of rogue planets or brown dwarfs. Extensive surveys have ruled that out. The leading theory is that dark matter is a new, exotic type of elementary particle, one that interacts with ordinary matter and light only through gravity, making it completely invisible and nearly undetectable. Candidates like WIMP, weakly interacting massive particles, or actions are the subjects of intense, ongoing research in massive underground detectors and particle colliders. The shape and distribution of these halos provide crucial clues in this hunt. For instance, computer simulations based on the theory that dark matter is cold and moves relatively slowly predict that halos should have very dense, cusp Y centers and vast numbers of smaller sub-halos orbiting within larger ones like satellites around a planet. Yet observations of the actual distribution of matter within galaxies sometimes show smoother cores, a slight but persistent discrepancy that has led some physicists to propose alternative theories, such as warm, dark matter, or even more exotic models that involve a subtle modification of the laws of gravity itself. This invisible architecture does more than just hold galaxies together. It dictates the fate of the universe. The total amount of dark matter determines the strength of gravity's pull, which fights against the expansion driven by dark energy. By mapping the distribution of these halos through their gravitational effects by watching how they bend light from distant galaxies in a process called gravitational lensing, or by tracing the flow of galaxies toward their centers, we are essentially taking an X-ray of the cosmos, revealing the hidden structure that binds everything. The dark matter halos are the ultimate cosmic puppeteers, and every single galaxy, from our own Milky Way to the distant giant arc, is dancing to their tune. They are the most abundant structures in the universe, and solving their mystery is the first step toward truly understanding the cosmos we call home. But if dark matter halos form the hidden scaffolding of the cosmos, then the cosmic web filaments are the magnificent architecture built upon it, the vast, thread-like rivers of dark matter and galaxies that weave the entire universe together into a single, interconnected whole. We've explored the dense clusters and the empty voids, but these are merely the nodes and the holes in this grand design. The filaments are the true connectors, the cosmic highways that channel the flow of matter and energy across billions of light years, and their discovery has completely reshaped our understanding of the universe's large-scale structure. For a long time, our view of the cosmos was like looking at a map of the world that only showed the cities and the oceans, but none of the roads, rivers, or mountain ranges that connected them. We could see galaxies and clusters, but their arrangement seemed random. It wasn't until large-scale galaxy surveys, like the Sloan Digital Sky Survey, began mapping the three-dimensional positions of millions of galaxies that the true pattern emerged. What appeared as a scattered collection of islands was in fact a vast, intricate network, a cosmic web. At the heart of this web are the filaments, immense, slender threads of dark matter that stretch between the great clusters and superclusters, tracing the outlines of the universe's largest empty void. Along these filaments, galaxies are strung like pearls on a necklace, drawn by gravity toward the dense clusters at the intersections. The scale of these structures is almost beyond human comprehension. A single filament can stretch for hundreds of millions of light years, yet be only a few million light years thick. They are not solid ropes, but rather the densest pathways in the cosmic web where the gravitational pull is strongest. It is within these filaments that the story of galactic evolution is written. As gas flows along these dark matter highways, it cools and condenses, providing the fuel for new stars to form and for galaxies to grow. This makes filaments not just passive structures, but active conduits, channeling the raw materials of creation from the barren voids into the bustling metropolises of galaxy clusters. They are the universe's supply lines, and without them, the great clusters we see today could never have formed. However, the very existence and properties of these filaments present a significant challenge to our models of cosmic evolution. Our most sophisticated computer simulations, which model the behavior of dark matter and the influence of gravity over billions of years, do a remarkable job of predicting the overall web-like structure. But when we look closely at the real universe, the filaments appear sharper, denser, and more defined than many simulations predict. This discrepancy suggests that our understanding of the complex physics within these environments, especially how normal gas behaves under such extreme conditions, is still incomplete. The gas flowing along these filaments is not smooth, it is turbulent and clumpy, and it interacts with magnetic fields and cosmic rays in ways we are only beginning to understand. Studying these faint structures is one of the most difficult tasks in modern astronomy, since the filaments themselves are primarily composed of invisible dark matter and extremely hot, diffuse gas that emits little light. We cannot observe them directly. Instead, astronomers must use clever indirect methods. One powerful technique is to observe the light from distant quasars. As this brilliant light passes through a filament on its way to Earth, the hot gas within the filament absorbs specific wavelengths, leaving a unique fingerprint in the quasar spectrum that we can detect. Another method is to use a phenomenon called gravitational lensing. The immense mass of a filament bends the fabric of space-time, minutely distorting the images of thousands of background galaxies. By meticulously mapping this subtle distortion, we can literally trace the outline of the invisible filament, creating a map of the unseen. This incredible network does more than just challenge our models. It reveals a universe that is fundamentally interconnected. The fate of a galaxy can be determined by its position within this web. A galaxy residing in a dense cluster will have a very different life, prone to violent collisions and having its gas stripped away, compared to a lonely galaxy spinning in isolation within a void. But a galaxy situated along a filament is on a journey, migrating from the quiet countryside toward the crowded galactic cities, transforming as it travels. The cosmic web filaments are the ultimate expression of the universe's dynamic nature, showing us that gravity's influence creates not just islands of matter, but an entire flowing, evolving cosmos, with every galaxy connected by these vast, invisible threads in the grand tapestry of space. While these invisible filaments and dark matter halos form the fundamental architecture of the cosmos, some structures are so vast and geometrically perfect that they seem to be etched onto the sky with a cosmic compass. After exploring the chaotic beauty of the cosmic web, we now turn our attention to a formation of breathtaking symmetry and scale, a structure so immense and so circular that its very existence pushes at the boundaries of what we believe is physically possible. This is the discovery of a colossal ring of galaxies, a formation often referred to as the giant ring or the ring of galaxies in zodiac, a celestial circle spanning an almost unimaginable 5.6 billion light-years across. To even begin to comprehend this scale, consider that the entire observable universe is roughly 93 billion light-years in diameter. This single ring, this one structure, accounts for roughly 6% of the entire observable cosmos. If it were visible in our night sky, it would sprawl across an area equivalent to 15 full moons. Its size is not its only astonishing feature. Its near-perfect circular geometry is what truly stuns astronomers. In a universe governed by gravity and dominated by chaotic collisions and mergers, the emergence of such a symmetrical, coherent shape on this scale is profoundly unexpected. It's like finding a single, perfectly formed soap bubble floating in the heart of a hurricane. The immediate and most compelling scientific explanation for such a ring points to a phenomenon known as baryonic acoustic oscillations. In the very first moments after the Big Bang, the universe was a searing hot, dense plasma of particles and light. In this primordial soup, pressure waves, much like sound waves, rippled outward from every density fluctuation. These waves traveled through the plasma until the universe cooled enough for atoms to form, around 380,000 years after the Big Bang, at which point the waves froze in place, imprinting a preferred scale on the distribution of matter. This scale became a kind of cosmic ruler about 500 million light-years long. As the universe expanded over billions of years, this ruler stretched, and we should see its signature as a slight statistical tendency for galaxies to be separated by this specific distance, creating a faint, bubbly pattern in the large-scale structure. The giant ring, however, presents a serious challenge to this elegant theory. While its size is in the general ballpark of what a stretched baryonic acoustic oscillation might look like, it is an order of magnitude larger than expected. Furthermore, baryonic acoustic oscillations don't typically manifest as single, isolated, and perfectly circular rings. They appear as a subtle statistical enhancement in the correlation function of galaxies, a faint whisper of a pattern across the entire sky. The giant ring is not a whisper, it is a scream. It is a coherent, singular structure that stands out starkly from the background, a lone, massive bullseye that seems too large and too defined to be easily explained by this standard model. Its perfection suggests it might be a relic of something that happened even earlier in the universe's history, or perhaps evidence of a process we haven't yet considered. This discrepancy has led scientists to explore more exotic and thrilling possibilities. One tantalizing theory involves cosmic strings, hypothetical one-dimensional defects in the fabric of space-time that could have formed during a phase transition in the universe's infancy. Think of them as cracks that formed as the universe cooled, incredibly dense and massive filaments thinner than a proton but stretching across the entire cosmos. The gravitational influence of such a string could theoretically create dense circular regions around it, potentially providing a template for the ring of galaxies we observe today. While still speculative, the discovery of the giant ring gives a compelling reason to take such ideas more seriously, as it could be the first tangible evidence for physics operating at energy scales far beyond anything we can recreate in a particle collider. The existence of this ring forces a profound cosmological dilemma. If it is a baryonic acoustic oscillation, then our understanding of that process and the initial conditions of the universe must be significantly revised to account for such a massive and distinct feature. If it is not, then we must be open to the possibility of entirely new and exotic physical processes that can sculpt the cosmos on scales we previously thought were impossible. The giant ring is more than just a list of galaxies. It is a question written in starlight, a circular argument etched across billions of light years that challenges us to either refine our theories or imagine a universe far stranger and more structured than we ever believed. Yet as we contemplate the vast, seemingly serene geometry of the giant ring, we are reminded that our universe is also a place of unimaginable violence and raw power, where titanic forces collide and reshape the cosmos. If that ring represents an almost theoretical perfection, then our next destination is a scene of cosmic carnage so extreme it defies belief. This is the story of the galaxy cluster known as El Gordo, which translates fittingly to the Fat One in Spanish. Officially designated ACDCLJ0124915, this isn't just a large gathering of galaxies. It is the most massive, the hottest, and the most energetic cluster known to exist in the distant universe, a colliding behemoth whose very existence pushes our understanding of physics to the absolute limit. Located a staggering 7 billion light-years away, we are seeing El Gordo as it was when the universe was barely half its current age. Its discovery itself was a marvel of modern observational techniques. It wasn't found with optical telescopes, but by detecting its profound shadow on the cosmic microwave background. As the faint light from the Big Bang's afterglow passes through the superheated gas that permeates the cluster, electrons within that gas scatter the photons in a specific way, a phenomenon known as the Sunyaev-Zeldovich effect. This creates a cold spot in the CMB map, and El Gordo's shadow was so deep and so pronounced that it immediately signaled the presence of something truly colossal. Follow-up observations with the Chandra X-ray Observatory then revealed the full, terrifying splendor of this cosmic battlefield. What they saw was not a serene, settled cluster, but two distinct subclusters of galaxies in the aftermath of a high-speed, head-on collision. The scene is one of pure chaos. The system is enveloped in a cloud of gas heated to a record-breaking 200 million degrees Celsius, so hot that it glows not in visible light, but in intensely powerful X-rays. This searing hot plasma has been torn apart from the galaxies themselves by the violent forces of the impact, creating a distinct cometary shape that streams behind the collision like a cosmic wake. But the true mystery of El Gordo lies not in what we can see, but in what we must infer from its incredible motion. By carefully measuring the separation between the dark matter, the hot gas, and the galaxies within the cluster, each of which behaves differently in a collision, astronomers were able to reconstruct the event. Their conclusion was staggering. These two subclusters must have slammed into each other at a velocity exceeding 2 million miles per hour. This incredible speed is the heart of the problem. For our current models of cosmic structure formation, this is almost too fast. The prevailing lambda cold dark matter model predicts how quickly structures should grow under the relentless pull of gravity. While large clusters are expected to form through mergers, the calculated gravitational pull from the visible mass in the early universe simply doesn't seem sufficient to accelerate such enormous concentrations of matter to the insane velocity we observe in El Gordo. It's as if we found evidence of a prehistoric avalanche that moved faster than the force of gravity alone could possibly explain. This discrepancy suggests that our simulations might be missing a crucial piece of the puzzle, perhaps related to the exact nature of the dark energy that was driving the universe's expansion at that epoch. However, El Gordo's greatest contribution to science may be the extraordinary window it provides into the behavior of dark matter itself. The cluster acts as a perfect natural laboratory for studying how this mysterious substance interacts. During a collision, the different components of a cluster behave in telltale ways. The clouds of hot gas made of normal matter slam into each other and slow down due to electromagnetic friction, creating that dramatic, lagging wake of X-rays. The galaxies, mostly empty space, pass through each other largely unaffected, and the dark matter, which does not interact with itself or normal matter through any force except gravity, should also simply pass through the collision unscathed. This is precisely what observations of El Gordo and other clusters like the Bullet cluster have shown. By mapping the cluster's total mass using the technique of gravitational lensing, seeing how its gravity distorts the light of more distant galaxies, astronomers can pinpoint where the dark matter is. In El Gordo, the dark matter is clearly separated from the lagging hot gas, proving that it is effectively sticky only through gravity and collisions without any detectable non-gravitational interactions. This confirmation is a monumental step forward. It rules out entire classes of alternative theories to dark matter that proposed it might have complex interactions. The collisionless behavior seen in El Gordo's dark matter components strongly supports the idea that it is indeed a fundamentally new type of particle. Furthermore, the sheer amount of dark matter required to bind this high-speed system together is immense, providing some of the most compelling indirect evidence for its existence and dominance in the universe's mass budget. El Gordo is more than just a record-breaking cluster. It is a cosmic crash test that has allowed us to conduct experiments on dark matter on a scale no human laboratory could ever achieve, providing crucial evidence for the existence of an invisible universe that shapes everything we see. But if the violent collision of El Gordo showcases gravity's awesome power to pull matter together, there is another, more mysterious force operating on an even grander scale, working in direct opposition to the relentless pull of gravity. This force doesn't build structures, it actively dismantles them, sculpting the cosmos not through attraction, but through repulsion. We are talking about the most profound enigma in modern physics, dark energy, and its astonishing repulsion effect that is reshaping the very fabric of the universe on the largest scales. For most of human history, we believed the universe's expansion was slowing down. After the initial thrust of the Big Bang, the collective gravitational pull of all the matter in the cosmos was thought to be acting like a cosmic brake, gradually decelerating the outward rush of galaxies. This was the prevailing view until the late 1990s, when two independent teams of astronomers made a discovery so shocking it earned them the Nobel Prize. By studying distant supernovae to measure the expansion rate over cosmic time, they found that the universe's expansion isn't slowing down at all, it is accelerating. Something is actively pushing galaxies apart, and that something has been dubbed dark energy. This isn't just a new force, it's a fundamental rewrite of the rules, an anti-gravity effect that dominates the cosmos. This repulsive force doesn't work like anything we experience in our daily lives. We can think of the universe's space-time as a vast, elastic fabric. Gravity is the effect created when matter dimples or warps this fabric, creating wells that other objects roll into. Dark energy behaves differently. It appears to be an intrinsic property of empty space itself, a constant energy density that causes the fabric of space-time to stretch and expand at an ever-increasing rate. The more the universe expands, the more space there is, and the more dark energy there is to cause even more expansion. It's a runaway feedback loop of creation, where nothingness itself generates a repulsive force that overwhelms gravity's pull. On the largest scales, this creates a cosmic tug-of-war where the outcome is predetermined. Gravity wins locally, binding galaxies and clusters, but dark energy wins globally, governing the motion of the entire cosmos. The most dramatic and visible impact of this repulsion effect is on the evolution of the largest structures we've explored, the cosmic voids and superclusters. Voids like the Boots void are not simply empty because matter was never there. They are actively being made emptier and larger by dark energy. Within these vast underdense regions, the gravitational pull is already weak. Dark energy seizes this advantage, causing the space inside voids to expand faster than the global average, effectively stretching them out and evacuating them even further. It's as if the universe is blowing gigantic bubbles, with dark energy providing the breath that inflates them. This process shepherds the remaining matter toward the edges, sharpening the boundaries between the empty voids and the dense filaments of the cosmic web. The voids are not passive holes, they are dynamic, growing entities, and dark energy is the engine of their growth. Conversely, dark energy's repulsive force places an ultimate limit on the growth of the largest gravitationally bound structures like the superclusters. For billions of years, gravity has been patiently pulling superclusters like Laniakea together, but dark energy acts as a cosmic regulator. While these structures are still bound by their own gravity, their future growth is now severely curtailed. The accelerating expansion is effectively isolating superclusters from one another. In the far future, galaxies outside our local gravitational sphere of influence will be pushed away by the expanding space between us faster than their light can ever reach us, disappearing from our observable universe forever. Dark energy has effectively drawn a border in the cosmos, defining the maximum size a structure can ever achieve and condemning the universe to a future of increasing isolation and darkness. This bizarre behavior directly contradicts our classical expectations based on gravity alone. The standard model of cosmology, lambda cold dark matter, incorporates both the attractive force of cold dark matter and the repulsive force of dark energy, represented by the Greek letter lambda. This model has been incredibly successful at predicting the large-scale structure we see, but the nature of dark energy itself remains perhaps the greatest unsolved problem in physics. Is it a true cosmological constant, as Einstein once proposed and then discarded as his greatest blunder? Or is it a dynamic field that changes over time, known as quintessence? The answer will determine the ultimate fate of the entire universe: a gradual, cold expansion into nothingness, or a potentially more violent end known as the Big Rip, where the repulsive force eventually becomes so strong that it tears apart galaxies, solar systems, and even atoms themselves. The dark energy repulsion effect is not something we can see in a telescope. It is inferred from its monumental impact on the geometry and destiny of the cosmos. It is the silent, dominant architect of the universe's largest structures, a mysterious pressure in the vacuum of space that is tirelessly working against gravity's pull, ensuring that the cosmos we see today is merely a transient phase in an epic story of construction and dissolution. But for all the monumental forces shaping the universe on the grandest scales, from dark energy's repulsion to the collisions of galaxy clusters, some of the most profound mysteries are written in the intricate structures of individual galaxies themselves. After exploring the vast, invisible architecture of the cosmic web, we now turn our gaze inward to the beautiful pinwheels of stars that have long captivated astronomers. Spiral galaxies like our own Milky Way are often pictured as serene, symmetrical whirlpools. Yet, a closer look reveals that a majority of them are not perfect spirals at all. They possess a striking and mysterious feature: a massive, straight bar cutting directly through their central cores, a cosmic skeleton around which the spiral arms themselves are wrapped. These galactic bars are not rare oddities, they are the rule rather than the exception, and their formation, evolution, and persistence are forcing us to rewrite the story of how galaxies live and die. So what exactly is a galactic bar? Imagine taking the central bulge of a spiral galaxy and stretching it out into a rigid, elongated structure made of billions of stars, gas, and dust. This bar can be huge, often stretching for tens of thousands of light years. It isn't a static structure, it rotates as a single, solid-like unit, orchestrating the flow of material within the entire galaxy. The spiral arms we so admire often don't begin at the very center. Instead, they unwrap from the tips of this central bar, like ribbons streaming from the ends of a baton twirled by a giant. Our own Milky Way is now confirmed to be a barred spiral, a fact that changes our understanding of our own galactic home. The prevailing theory for how these bars form is a fascinating story of self-organization and gravitational instability. A young, pristine disk galaxy might start as a simple, featureless pancake of stars and gas, but it doesn't stay perfect for long. Small asymmetries, perhaps caused by a minor interaction with a neighboring galaxy or even just the inherent clumpiness of the disk, can create a gravitational disturbance. This disturbance acts like a seed. Stars in the crowded central regions begin to follow elongated, oval-shaped orbits instead of perfect circles. As more stars get caught in this pattern, their collective gravity reinforces it, amplifying the effect. It's a gravitational feedback loop where the bar essentially builds itself, growing stronger and more pronounced over time. Think of it like a traffic jam on a cosmic scale. Once a few stars start moving in a certain way, they force others to fall into line, creating a dense, slow-moving structure that governs the flow of everything around it. Once formed, the bar becomes the galaxy's primary engine for internal evolution, and its influence is transformative. The rotating bar acts as a vast cosmic mixer, churning the galaxy's material with immense gravitational leverage. It funnels huge quantities of gas and dust from the outer regions of the disk inward toward the galactic center. This influx of fresh fuel can trigger intense bursts of new star formation, both within the bar itself and in the central nucleus. In some cases, this relentless delivery of gas can feed and power the supermassive black hole lurking at the very heart of the galaxy, potentially activating it as a brilliant quasar. In this way, a bar can determine the very life cycle of a galaxy, turning a quiet, steady state into a period of vibrant, violent activity, and ultimately shaping the mass and character of its central black hole. However, the long-term persistence of these bars presents a serious puzzle for astrophysicists, one that directly involves the mysterious nature of dark matter. According to early simulations, these elegant structures should be inherently unstable. The same gravitational forces that create the bar should, over hundreds of millions of years, cause it to wind up ever tighter, eventually dissolving into a larger, featureless central bulge. The fact that we observe so many ancient, well-defined bars in the universe today means something must be holding them together, providing a stabilizing influence. That something is almost certainly the hidden halo of dark matter that envelops every galaxy. The current leading theory suggests that dark matter plays a dynamic role in this galactic drama. As the stellar bar rotates, it creates a gravitational wake, much like a boat moving through water. The invisible particles of dark matter in the halo are thought to respond to this wake, potentially slowing down the bar's rotation or locking into a stable resonance with it. This interaction between the visible bar and the invisible dark matter halo could provide the necessary gravitational scaffolding to prevent the bar from self-destructing. Therefore, the very existence of a long-lived galactic bar acts as a powerful indirect probe of the properties of dark matter itself. It suggests that dark matter particles must be cold, meaning they move relatively slowly, allowing them to settle into a stable, structured halo that can interact gravitationally in this precise way. If dark matter were hot or moved too fast, it wouldn't be able to form these stable halos, and the bars we see would not persist. The humble bar, a structure we can see, is thus providing crucial evidence for the nature of the dark matter we cannot. But the elegant, self-organizing dance of a galactic bar is just one way a galaxy can shape its destiny. For others, the story is far more explosive. A tale of raw power unleashed from the deepest, darkest heart of a galaxy, reaching out to touch the very void between galaxies. This brings us to the dramatic and colossal radio lobes of Centaurus A, a nearby active galaxy that serves as a breathtaking laboratory for studying the most extreme phenomena in the universe. If you could see the sky with radio eyes, Centaurus A would not appear as a simple spiral or elliptical. it would dominate the view as a titanic dumbbell-shaped structure with two gigantic, glowing lobes of energy stretching over 1.4 million light-years from end to end. That is a distance 15 times greater than the span of our entire Milky Way galaxy. These are not made of stars, they are immense balloons of magnetized plasma, and they represent one of the most powerful and sustained eruptions ever witnessed, a constant reminder that a galaxy's core can become a cosmic blowtorch of unimaginable force. The engine for this incredible spectacle is the supermassive black hole at the center of Centaurus A, a beast weighing in at about 55 million times the mass of our Sun. Unlike our own galaxy's relatively quiet central black hole, the one in Centaurus A is a voracious feeder, as vast quantities of gas, dust, and even entire stars are torn apart and spiral into its accretion disk. The intense gravitational and frictional forces heat this material to billions of degrees, causing it to glow brilliantly across the electromagnetic spectrum. But not all this matter falls in. Some of it, channeled by incredibly powerful magnetic fields, is focused and blasted away from the black hole's poles at nearly the speed of light, forming two opposing jets of energetic particles. These jets are so powerful and focused that they punch right through the surrounding galaxy, shooting out into intergalactic space. The radio lobes we see are the result. They are the expanding shock fronts where these ultra-relativistic jets finally slam into the incredibly thin gas that permeates the space between galaxies, plowing it aside and inflating these colossal, radio-emitting bubbles. The sheer size and energy of these lobes pose a direct challenge to our models of jet formation and longevity. We understand the basic physics of accretion and jet launching, but the stability of these jets over such vast distances is a profound mystery. How do they remain so tightly focused for over 500,000 light-years without dispersing into a useless fog? The magnetic fields within the jets must be incredibly strong and well-ordered, acting like an invisible pipeline that keeps the particles on a straight and narrow path. Furthermore, the energy required to inflate these lobes and keep them glowing for millions of years is almost beyond calculation, dwarfing the combined output of every star in the galaxy. This forces us to consider that the feeding process of the central black hole is not a steady trickle, but likely a series of monstrous, episodic outbursts, each injecting a fresh surge of energy into the lobes and causing them to grow even larger. The impact of these structures extends far beyond their own spectacular appearance. They are a dominant force in the ecology of their entire galactic neighborhood. This process, known as AGN feedback, is now considered crucial to galaxy evolution. The energy blasting from the lobes heats the surrounding intergalactic gas, preventing it from cooling and falling back into the galaxy to form new generations of stars. In this way, the central black hole acts as a cosmic regulator, its own outbursts eventually shutting off the very fuel supply that feeds it. It's a self-limiting cycle that helps explain why we don't see galaxies growing indefinitely larger. The radio lobes of Centaurus are a stunningly clear example of this feedback in action, a giant thermostat helping to shape the growth and ultimate fate of its host galaxy. They show us that a galaxy is not an island. Its most violent internal processes can reach out across millions of light-years, carving its signature into the cosmos and dictating the conditions for galactic life and death. Now, as we shift our gaze from the violent outbursts of galactic cores to our own galactic neighborhood, we encounter a structure of breathtaking scale and elegance that has been streaming right over our heads for billions of years. This is the Magellanic Stream, a vast and ethereal river of gas that arches across the southern celestial hemisphere, a cosmic bridge connecting our Milky Way to its two largest satellite galaxies, the Large and Small Magellanic Clouds. If you could see this neutral hydrogen in visible light, it would be the most prominent feature in our night sky, a shimmering ribbon stretching over an incredible 600,000 light-years from end to end. Yet, despite its immensity and proximity, This stream has been the source of a decades-long mystery, a puzzle that challenges our very understanding of how galaxies interact and evolve. The story of its discovery is a classic tale of seeing the unseen. The stream itself was first detected in the early 1970s not by optical telescopes, but by radio telescopes tuned to the specific wavelength that cold hydrogen gas emits. Astronomers were mapping the sky, and this enormous, coherent structure of gas simply emerged from the data, a colossal but faint signature that had been invisible to every other form of observation. Its shape was unmistakable, a long, trailing arm that leads the Magellanic Clouds in their orbit around our galaxy, followed by a shorter, leading arm that seems to race ahead of them. This entire gaseous structure is like the wake of a ship, but on a cosmic scale, tracing the path of these two dwarf galaxies as they are pulled by the Milky Way's immense gravity. For a long time, the leading theory for its origin seemed elegantly simple: tidal forces. The idea was that as the large and small Magellanic Clouds have swung around the Milky Way, our galaxy's gravitational pull has been acting like a tremendous tide, ripping gas and stars from the smaller galaxies. This stripped material would then trail along behind them, much like a comet's tail, creating the long, filamentary stream we observe. This explanation fit neatly with our models of galactic dynamics and provided a clean, intuitive picture of how satellite galaxies can be slowly dismantled by their larger hosts. However, as observations grew more precise, a serious problem emerged with this tidy narrative. The sheer amount of gas in the stream is staggering. It contains hundreds of millions of times the mass of our Sun in hydrogen alone. When scientists ran detailed simulations of the tidal interaction between the clouds and the Milky Way, they found that gravity alone couldn't account for stealing that much material. The tidal forces simply weren't strong enough to pull out such a massive quantity of gas, especially from the smaller, more gravitationally bound small Magellanic Cloud. The simulations kept producing a stream that was far too short and contained far too little gas compared to the magnificent structure we actually observed. This discrepancy meant that a fundamental piece of the physics was missing from our models. This is where the mystery deepens into far more exciting territory. Astronomers began to propose a more dramatic and dynamic origin story: ram pressure stripping. This process doesn't rely solely on gravity. Instead, it involves the clouds plowing through the Milky Way's own extended halo of hot, diffuse gas. Imagine the Magellanic Clouds as ships sailing not through empty space, but through a thin, intangible atmosphere. As they move, this tenuous galactic halo exerts a pressure on the gas within the dwarf galaxies, much like the wind against your face when you stick your hand out of a moving car window. For the clouds, this wind can be powerful enough to literally blow the gas right out of them, sweeping it into the long, trailing stream we see today. This idea gained traction because it could much more efficiently explain the vast quantity and distribution of gas in the stream. But the most revolutionary theory combines both ideas and adds a spectacular new layer: that the stream is not just the product of the Milky Way's influence, but also of a dramatic past interaction between the two Magellanic Clouds themselves. Observations from telescopes like the Hubble Space Telescope have confirmed that these two galaxies are not just independent satellites. They are a bound pair, orbiting each other as they together orbit the Milky Way. Billions of years ago, they likely had a close encounter, a gravitational dance that would have violently stirred up their gas, making it far easier for subsequent tidal forces and ram pressure to pull it all out. In this scenario, the Magellanic Stream is the result of a cosmic triple threat, a gravitational tug of war involving three players, not two. The structure of the stream itself provides the crucial evidence that is challenging and refining these models. Its complex filamentary nature, with clumps and twists along its length, doesn't look like a simple, smooth tidal tail. It looks dynamic and messy, the signature of a violent and multi-stage history. Furthermore, recent observations have detected not just neutral hydrogen, but also a surprising amount of ionized hot gas within the stream, suggesting it is interacting with the Milky Way's halo in active and complex ways we are only beginning to understand. Studying the Magellanic Stream is like reading a history book of our local galactic group. Its composition, temperature, and velocity hold forensic clues to the past orbits of the Magellanic Clouds, the density of the Milky Way's halo, and the very nature of the gases that form the building blocks of stars. It is a living laboratory happening right on our cosmic doorstep, a continuous experiment in galactic evolution whose results are still coming in. This vast ribbon of gas is more than a beautiful celestial feature. It is a dynamic and evolving structure, a key to understanding the life cycle of galaxies and the invisible forces that continuously reshape our corner of the universe. Just as we begin to process the immense scale of the Magellanic Stream flowing through our own galactic neighborhood, our journey takes a monumental leap outward to a structure of such staggering breadth that it redefines the very meaning of cosmic grandeur. Imagine a wall of galaxies so vast that it would take light over 1.37 billion years just to travel from one end to the other. This is not a metaphor or a theoretical construct. This is the Great Wall of Galaxies in Pisces Cetus, a recently discovered titan that stands as one of the largest contiguous structures ever identified in the observable universe. Its existence was confirmed in 2021, not through a single dramatic image, but through the meticulous work of astronomers piecing together large-scale surveys, slowly revealing a filament of galaxies on a scale that many theorists believed was impossible. What makes this wall so profoundly challenging to our understanding of the cosmos is not merely its size, but its specific orientation and remarkable coherence. Spanning an area of the sky that encompasses the constellations of Pisces and Cetus, this structure isn't a random, scattered collection of galaxies. It is a highly organized, dense superhighway of matter, a filament within the cosmic web that exhibits a level of large-scale structure that seems to defy the expected randomness of the universe. According to the foundational cosmological principle, when you zoom out far enough, the universe should appear roughly the same in every direction, with matter distributed in a largely homogeneous and isotropic manner. The presence of a single, well-defined structure that occupies such a significant fraction of the observable universe directly confronts this principle. It suggests that the universe may not be as smooth and uniform as we have long assumed, but instead possesses textures and features on scales we are only just beginning to appreciate. The implications of its scale are equally staggering for our models of cosmic evolution. Our current understanding, based on the lambda cold dark matter model, places a theoretical upper limit on how large a single structure can grow. This limit is dictated by the age of the universe and the speed at which gravity can pull matter together over vast distances. The Great Wall in Pisces Cetus pushes right up against this limit, and many would argue it smashes straight through it. For gravity to have assembled such an immense structure in the roughly 13.8 billion years since the Big Bang, the initial seeds from which it grew must have been incredibly, perhaps anomalously, dense. Its very presence forces cosmologists to consider whether our standard model of the universe's infancy needs a significant revision, or if there are other, unknown physical processes that can accelerate the growth of structure on these truly gargantuan scales. This Great Wall acts as a colossal fossil, preserving information about the conditions of the very early universe. By studying its dimensions, the distribution of its galaxies, and its overall geometry, astronomers are effectively performing a forensic investigation into the primordial density fluctuations that were imprinted upon the cosmos during the period of inflation, a fraction of a second after the Big Bang. The wall's exceptional size suggests that those initial fluctuations might have had much more pronounced variations than our best models predict, with some regions of the infant universe being significantly denser than others. This isn't just a curiosity, It is a fundamental clue that could help us understand the physical mechanisms that operated at energies trillions of times higher than anything we can recreate in particle colliders on Earth. Ultimately, the Great Wall of Galaxies in Pisces Cetus is more than just another entry in a catalogue of large structures. It is a profound challenge and a beacon of discovery. It stands as a silent, monumental question mark etched across the sky, compelling us to question long-held assumptions and daring us to imagine a cosmos that is far more structured, complex, and wondrous than we ever believed possible. Its discovery reminds us that every time we build a more detailed map of the universe, we are likely to find new wonders that force us to redraw the boundaries of our knowledge and rewrite the story of cosmic evolution. Yet, even as we map these immense, fossilized structures from the early universe, a far more intimate and immediate cosmic crisis is unfolding, one that strikes at the very heart of our ability to measure reality itself. This is not a puzzle about what happened billions of years ago, but about what is happening right now. At the center of this modern maelstrom is a deceptively simple number, the Hubble constant. This figure represents the current expansion rate of the universe, the speed at which galaxies are receding from us. For decades, astronomers have worked to pin down this number with ever-increasing precision, believing it to be a fundamental parameter of our cosmos. But a troubling discrepancy has emerged, a disagreement so stubborn and significant that it has blossomed into a full-blown crisis in cosmology known as the Hubble tension. The conflict arises from two powerful, yet seemingly irreconcilable, methods of measurement. The first approach is local and direct. Astronomers use brilliant, predictable stellar explosions called Type 1, a supernova, as standard candles. By knowing their true, intrinsic brightness and measuring how dim they appear from Earth, they can calculate precise distances to their host galaxies. Combining this distance with measurements of how fast those galaxies are moving away from us, their redshift, provides a direct calculation of the expansion rate. This method, refined over years with data from telescopes like Hubble, gives us a very specific number. The second method takes a completely different tack, looking back to the very beginning. It uses the exquisitely detailed map of the cosmic microwave background, the afterglow of the Big Bang, as captured by the Planck satellite. This fossilized light reveals the exact conditions of the infant universe. By plugging these initial conditions into our standard model of cosmology, the lambda-cold dark matter model, scientists can run the clock forward 13.8 billion years and predict what the expansion rate should be today. This method is incredibly powerful and self-consistent, but it predicts a value for the Hubble constant that is significantly slower than the one measured from local supernova. The difference might sound small, just a few kilometers per second per megaparsec, but its implications are monumental. This isn't a minor rounding error. It's a persistent and statistically significant gap that has withstood intense scrutiny and improved measurements. It's as if you used two different, impeccably calibrated rulers to measure the same table, and each time they gave you a different length. The unavoidable conclusion is that something is fundamentally wrong. Either one of our measurement techniques is suffering from an unknown systematic error we haven't accounted for, or our standard model of cosmology is incomplete. The latter possibility is why this tension is so electrifying and unsettling for physicists. This is where the possibility of unknown large-scale structures enters the debate as a potential solution. Could our local cosmic environment be skewing our measurements? We previously discussed the KBC void, the suggestion that we may reside in a vast underdense region of space. If true, this could provide an elegant explanation. In a giant void where gravitational pull is weaker, the local expansion rate would be faster than the global average. Our measurements from nearby supernova would be accurately measuring this faster local expansion, while the Planck measurement from the CMB would be giving us the slower, true global rate. The tension wouldn't be an error, but a clue, a revelation that our vantage point is not typical. forcing us to account for our place in a textured and inhomogeneous cosmos. However, many cosmologists find this solution unsatisfactory, arguing that the scale of void required to create the observed discrepancy is implausibly large. This has led to more exotic proposals that involve rewriting the laws of physics. Perhaps dark energy is not a constant force but a dynamic field that has changed strength over the history of the universe. Maybe dark matter possesses some strange, unknown properties that cause it to interact in new ways. Or perhaps there exists an entirely new type of relativistic particle that flooded the early universe, subtly altering the rate at which structures formed and thus changing the predicted expansion history. Some have even entertained the radical notion that the Hubble tension is the first observational hint that we need to modify Einstein's theory of gravity itself on the largest scales. The most intriguing recent development adds yet another layer of mystery. Some studies have suggested that the expansion rate might not be the same in all directions, a concept known as anisotropy. The idea that the universe could have a preferred axis, a cosmic directionality where expansion proceeds at different speeds, would shatter a foundational pillar of cosmology and force a complete reimagining of our models. While the evidence for this is still tentative and highly controversial, its mere consideration highlights the depth of the crisis. The Hubble tension is no longer just a debate about a number. It is a profound invitation to explore new physics, to question our most basic assumptions about the uniformity of the universe, and to acknowledge that the cosmos may hold complexities we are only just beginning to perceive. And this brings us to a process that is both brutal and beautiful, a fundamental mechanism of growth that has shaped every large galaxy we see, including our own. We've witnessed the colossal forces of dark energy and the explosive power of active galactic nuclei, but the story of a galaxy's life is also written in the silent, ghostly trails of its victims. This is the evidence for galactic cannibalism, a vivid testament to a universe where the large consume the small, and where the serene beauty of a spiral galaxy often masks a violent and hierarchical history of cosmic conquest. The classic peaceful image of galaxy formation, a giant cloud of gas gently cooling and condensing into a majestic spiral, is, we now know, only a small part of the story. The true narrative is far more dramatic. Our prevailing model of cosmic structure is known as hierarchical clustering. It posits that the universe built itself from the bottom up. The first structures to form after the Big Bang were small, dwarf galaxies. Over billions of years, drawn together by the relentless pull of gravity, these dwarfs merged, collided, and were consumed by larger galaxies, building the grand spirals and ellipticals we see today. Our Milky Way is not a pristine island universe. It is a cosmic metropolis built from the rubble of countless smaller galactic building blocks. And the evidence for this is not buried in the distant past. It is written in the stars above us right now. The most stunning and direct evidence for this ongoing cannibalism comes in the form of vast, delicate structures that wrap around galaxies like celestial spiderwebs, stellar streams. These are not streams of gas like the Magellanic Stream, but rivers of stars that have been torn from their parent dwarf galaxies and globular clusters by the immense tidal forces of a larger galaxy. As a small satellite galaxy orbits a giant like the Milky Way, the gravitational pull is stronger on the side closer to the host than on the far side. This difference in force, the tidal force, stretches the smaller galaxy, eventually pulling it apart. Its stars are not destroyed. Instead, they are flung into long, looping orbits around the predator galaxy, forming streams that can persist for billions of years, tracing the exact path of the destruction. The most famous example is the Sagittarius dwarf spheroidal galaxy. Discovered in 1994, it is currently in the process of being devoured by the Milky Way. Our galaxy's gravity has stretched it into a magnificent arc that completely encircles us, a ring of stars that we are currently passing through. We are, quite literally, swimming through the remnants of a galaxy we are in the act of consuming. Other streams with names like GD1 and the Phoenix Stream crisscross our galactic halo, each one the ghostly fossil of a separate, ancient meal. These structures are incredibly faint and difficult to detect, requiring sophisticated digital sky surveys to pick their subtle starlight out from the brilliant backdrop of the Milky Way. Their very existence is a permanent record of our galaxy's violent growth, but the evidence isn't just outside the galaxy, it's also in its very heart. The chaotic, swollen central bulges of many large galaxies, including our own, are thought to be the product of numerous past mergers. When two galaxies of similar size collide, the event is catastrophic. Their delicate spiral structures are shredded, and their stars are thrown into random, disordered orbits, creating a featureless elliptical galaxy or a bulge-dominated spiral. The larger of the two galaxies effectively digests the smaller one, absorbing its stars, its gas, and even its dark matter halo. Computer simulations show that without this hierarchical merging, galaxies would be far smaller and thinner than they are. Cannibalism is essential for building their massive central components. This violent history presents a significant challenge to the old, smooth models of galaxy formation. The fact that we see these stellar streams at all means that the galactic halo is not a smooth, well-mixed cloud of ancient stars. It is lumpy and structured, a palimpsest still bearing the scars of incomplete digestion. Furthermore, the stars within these streams often have distinct chemical fingerprints. Stars formed in different dwarf galaxies can have different ratios of elements based on the unique history of supernova that enriched their birth clouds. By studying the chemistry of stars in the halo, astronomers can often identify groups that share a common origin, like finding pieces of different puzzle boxes all mixed together. This allows us to perform galactic archaeology, reconstructing the sequence of mergers that built our galaxy and dating them by the motions and compositions of their stellar debris. The implications of galactic cannibalism extend far beyond our own Milky Way. We see its evidence everywhere. The giant elliptical galaxies at the hearts of dense clusters are the ultimate cannibals, having grown to immense sizes by consuming countless smaller neighbors. The very fact that large galaxies are surrounded by a swarm of dwarf satellites is a key prediction of the model. These are the leftover building blocks, the next meals waiting to be consumed. This process reveals a universe that is dynamic and evolutionary, where galaxies are not isolated islands but social creatures in a constant gravitational dance, a dance that often ends in a violent embrace and a cosmic feast. It is a humbling reminder that the majestic galaxy we call home is the product of a long and violent history, a giant whose growth has been fueled by the consumption of others, and whose past is forever written in the ghostly streams of stars that circle it in the dark. But if galactic cannibalism reveals the violent, hierarchical history of individual galaxies, then the phenomenon of Baryon acoustic oscillations takes us back to the very first moments of creation, to a time when the entire universe was a searing hot plasma, echoing with primordial sound waves that would forever dictate the large-scale arrangement of all matter. This is not a structure you can point a telescope at and see. It is a statistical ghost, a fossilized pattern imprinted on the distribution of galaxies across the cosmos. And it provides us with a standard ruler of such precision that it allows us to take the universe's vital signs in a way nothing else can. To understand these oscillations, we must journey back to the universe's first 400,000 years. At this time, the cosmos was not transparent but was a dense, opaque fog of protons, electrons, and light, a plasma so hot that atoms could not form. In this primordial soup, gravity was tirelessly trying to pull matter together into clumps, but it had a powerful opponent, the intense pressure of the light, which is made of photons. Imagine a region where matter begins to collapse under its own gravity. As it collapses, it grows denser and hotter, which increases the radiation pressure. This pressure eventually becomes so strong that it creates a powerful outward push, launching a spherical sound wave, a compression wave rippling outward through the plasma. This is the acoustic part. The baryon part refers to the normal matter, the protons and neutrons, that was caught in this wave surfing along with it. This cosmic tug of war between gravity's pull and radiation's push happened everywhere at once, creating a universe filled with these ringing, spherical density waves. This ringing continued until the universe expanded and cooled enough for a pivotal event, recombination. At this moment, electrons combined with protons to form the first neutral hydrogen atoms. Suddenly, the photons, which had been constantly scattering off the electrons, were set free. The universe became transparent, and that first flash of light is what we now see as the cosmic microwave background. But crucially, the sound waves froze in their tracks. The matter that had been gathered at the leading edge of each spherical wave was suddenly left stranded, creating a subtle preference for galaxies to form at a specific distance from one another. This distance became a permanent cosmic yardstick. This preferred scale is the key to everything. That frozen wave, the distance from the center of the original overdensity to the peak of the spherical shell, was about 500,000 light-years across at the moment it was frozen. Then, as the universe expanded over the next 13 billion years, this standard ruler stretched along with it. Today, that same preferred separation between galaxies, the echo of that primordial sound, has grown to a scale of about 500 million light-years. This means that if you were to take a census of millions of galaxies, you would find a slight statistical excess of pairs separated by this exact distance. It's as if the universe has a subtle grid-like pattern woven into its very fabric, a fossilized echo of its own infancy. This makes BAOs one of the most powerful tools in modern cosmology. By measuring this standard ruler at different distances, and therefore at different epochs in cosmic history, astronomers can precisely track how the expansion rate of the universe has changed over time. It acts as a calibration tool, allowing us to measure cosmic distances with incredible accuracy and independently confirm the values of key cosmological parameters, like the density of dark matter and dark energy. In many ways, it has become the gold standard for mapping the large-scale structure of the universe, a rigid template we can lay over galaxy surveys to see how the cosmos has been stretched and warped by the forces within it. However, recent ultra-precise measurements from projects like the Sloan Digital Sky Survey and the Dark Energy Survey have begun to reveal something curious. While the BAO signal is robust, its precise details sometimes don't align perfectly with the predictions of our standard lambda-cold dark matter model. The patterns are there, but their strength or their specific scale in certain directions can show faint, anomalous deviations. These are not yet definitive discoveries, but they are intriguing hints. They suggest that the primordial seeds themselves might have had more complex variations than we thought, or perhaps that dark energy is not perfectly uniform, but could have slight variations that subtly warp the fabric of space on the largest scales, distorting our cosmic ruler. These tiny discrepancies open a thrilling possibility that within this fossilized sound wave, we might find evidence for entirely new physics or hidden cosmic structures. Could these anomalies be caused by the gravitational influence of structures so vast they lie beyond our current observational horizon, similar to the proposed source of the dark flow? Or might they hint at something more fundamental, like a dynamic nature of dark energy or even a flaw in our understanding of gravity itself? The beauty of the baryon acoustic oscillations is that they provide such a clean, predictable signal that any deviation from that prediction is a glaring clue. They are the universe's own fingerprint, and by studying its unique walls and ridges with ever-increasing precision, we are not just measuring the cosmos, we are listening to its deepest secrets, hearing the faint echo of its first and most fundamental sound, a vibration that continues to shape everything we see. Yet after this grand tour across billions of light years, from the echoes of the Big Bang to the ghostly streams of our own galactic backyard, a single unifying truth emerges. Each of these 25 cosmic structures, in its own unique way, serves as a profound challenge to the very foundations of our understanding. They are not merely isolated curiosities. They are interconnected pieces of a much larger puzzle, a collective roar of dissent against the comfortable assumptions we've held for decades. The cosmological principle, the idea that the universe is uniform and homogeneous on the largest scales, is shaken to its core by the existence of titanic walls and immense voids that defy statistical probability. Our models of gravity and dark matter are rigorously tested by the violent collisions of galaxy clusters and the persistent rotation of galactic bars, forcing us to consider if we are missing a crucial piece of the physics that governs the cosmos. Even our most precise measurements of the universe's expansion rate are called into question, suggesting that our local vantage point may be far from typical or that entirely new physics is at work. These are not minor inconsistencies, they are glaring signposts pointing toward a reality far more complex, textured, and mysterious than our textbooks have ever described. What makes this journey so exhilarating is that it reveals science not as a static set of facts, but as a living, breathing process of discovery and humility. Each anomaly, each structure that shouldn't be there, is an invitation to dig deeper, to question more boldly, and to imagine more wildly. They remind us that the universe is under no obligation to conform to our human sense of order, and that the greatest revelations often come from the places where our models break down. The giants we've explored, from the Hercules-Corona Borealis Great Wall to the Dark Flow, are not in points. They are the beginning of new chapters in a story we are only just starting to write. They inspire a sense of awe not just for the scale of the cosmos, but for the human capacity to explore it, to push the boundaries of our knowledge, and to continually redefine our place in this vast, incredible universe. So we leave you with this question to ponder. As our telescopes grow more powerful and our maps of the cosmos become ever more detailed, what other impossible structures are waiting to be found? What other fundamental laws might be waiting to be rewritten? The greatest mystery of all may be that for every question we answer, the universe unveils 10 more, ensuring that the adventure of discovery will never truly end. We'd love to hear which of these cosmic structures you find the most mind-boggling. Was it the perfect ring of Hoag's object, the terrifying collision of El Gordo, or the haunting pull of the Great Attractor? Let us know your thoughts in the comments below, and if you've enjoyed this journey to the edges of understanding, be sure to subscribe so you don't miss our next exploration into the depths of space, time, and mystery.